Welcome back to part 15 of our technical training series on reliability engineering and risk assessment. Now that we have successfully walked through our reactor case study, the absolute best way to truly master these probabilistic risk assessment methodologies is through direct application. That is why in this session, we are providing you with a completely fresh, standalone practice example featuring a brand new system architecture for you to try out and model entirely on your own. Our new practice exercise centers around a cooling system design. The fundamental function of this system is to ensure continuous cooling to an external process loop via a dedicated heat exchanger, IEC. Let's trace the fluid path and control architecture from right to left as shown in the schematic. Cooling fluid enters the system from the right and immediately encounters a parallel, redundant boundary. The top line, or leg 1, is regulated by an electronic valve, EV1, and driven by an electric pump, EP1. The bottom line, or leg 2, acts as a redundant backup and mirrors this configuration with electronic valve EV2 and electric pump EP2. Downstream of each pump, check valves NRV1 and NRV2 are installed to block backflow and isolate the parallel lines. The streams then merge back into a single main line, passing through a flow sensor, FS1, before entering the HEX coils. The active control loop is managed by a central controller, CON1. The FS1 flow sensor continuously monitors the process and feeds its data back to CON1, which in turn commands the operation of both valves and both pumps. Let's dive into the operational logic and critical hardware dependencies that you will need to account for in your fault tree. Under normal conditions, the coolant is actively supplied exclusively via leg 1 using pump EP1. If leg 1 becomes unavailable for any reason, the flow sensor FS1 is designed to detect the resulting drop in the flow rate. Upon receiving this signal, the controller will automatically initiate a mitigation sequence. It will close valve EV1, open valve EV2, and start pump EP2 to bring the backup leg online. However, because the pumps and valves, EP1, EP2, EV1, and EV2, are all electrically operated, our reliability model must also incorporate the underlying electrical supply system. Looking at the electrical single-line diagram on the right, the power architecture is split into two distinct distribution buses. VITA specifically distributes power to the pumps, EP1 and EP2. It can be fed by the primary external grid through transformer T1 and circuit breaker C1, or by a backup diesel generator, DGN, through transformer T2 and breaker C2. Board B provides power to the motorized valves, EV1 and EV2. Similarly, it is fed from the grid side via transformer T3 and breaker C3, or from the emergency DGN side via transformer T4 and breaker C4. This shared electrical network introduces major common cause dependency structures to the exercise. A loss of board completely drops both pumps, while a failure of the external grid forces the system to rely entirely on the backup diesel generator. Keep these interactions in mind as you begin constructing your logic gates. Now let's define the explicit scope and core execution target for this standalone exercise. Your objective is to evaluate this system using deductive modeling. The fault tree top gate must be explicitly named total loss of cooling. The tables on the following two slides consolidate the exact basic event codes you need to map into your project workspace. For this final workshop, we are not going to give away the solution or reveal the generated cut sets in this video. Your task is to open the item toolkit, map out the system boundaries, link these parallel process lines to their shared electrical boards, and run the calculation engine yourself. Once you have completed your logic structure, leave a comment below the video and let us know how many cut sets you got and the list of cut sets generated with these basic events. You can also contact us directly, and we will let you know if your result is right or wrong. This is the ultimate way to test your skills and try it on your own to wrap up the series. Before we set you loose on this final challenge, we want to say a huge thank you to everyone who has joined us throughout this entire training series. We truly hope you've learned some valuable methodologies, formulas, and practical software skills to take into your own reliability engineering work. If you have any remaining questions about this exercise or any of the concepts we've covered along the way, please do not hesitate to contact us. Thank you once again for watching, and happy modeling.